for B is a double integral. This is the double integrals part of question 4. And so here's the question: evaluate the following double integral. And you can see we've given you this double integral where we've already specified for you the limits on the integral. So we haven't given you a region. A region is implied by these limits. So in principle, you're ready to go ahead and evaluate. Now, the slight glitch here, and you will see this on your actual exam also, will also have this feature, which is that we've ordered the variables of integration so that, in fact, there's a problem with this inner integral. So normally, if it's set up this way, you would start off the problem by evaluating the inner integral first, which means you're holding y fixed and you're integrating with respect to x. And you can see here, that's a problem here because cosine x squared does not have an antiderivative in terms of elementary functions. So, in other words, what function could we propose whose derivative is cosine x squared? There isn't one. So that's really a problem. So if it was cosine x, it would be fine because the integral, the antiderivative of cosine x would be sine x. So that's fine. But this x squared here, because of the chain rule of differentiation, gives us a problem. So in particular, if we suppose that the antiderivative was sine of x squared, we'd see right away that it doesn't differentiate to give cosine x squared. Let me just do that over here to emphasize this to you. So if we suppose that the antiderivative is sine x squared, so when we differentiate that again, in hopes of getting back to our integrand, that derivative is in fact cosine x squared times 2x by the chain rule. So in other words, we really need to have this extra 2x here, the derivative of the inner function, and we don't have it. So what we must do to alleviate this issue is to reverse the order of integration. So what we want to have instead is an integral, a double integral of cosine x squared, not dx dy, but dy dx, because that allows us to integrate with respect to y in the first instance, holding x fixed. So x being fixed, that's just a constant now, so we can integrate easily. So the problem now is that we need to get new limits of integration for this new ordering. To do that, we have to consider the region of integration. We get the region from the limits of the original integral. So that's what we must do first. We must get the region of integration so that we can get our limits correct. Note that if an integral is set up correctly, the outer integral will have only numbers, and anything inside that will only have limits that are functions of variables that are outside and that are therefore being held fixed. So in other words, we can't just switch these around. We do need to consider the region. So let's look at the region associated with this integral. So this integral implies that we're holding y fixed in the first instance. So let's just have a look at that and integrating with respect to x. So we're holding y fixed, so we're imagining taking slices of constant y, and on any such constant y, we're going from x equals y on 2 to x equals 1. So x equals y on 2 at the bottom. That's a straight line function through the origin. So this is x equals y on 2. And of course, normally we express that with y as the subject of the formula, y equals 2x. So we're going from x equals y on 2 to x equals 1 on any given slice. So here's x equals 1. So we'll do that. So we'll integrate this way. Then in y, our second variable, we'll be taking these slices from y equals 0 to y equals 2. So 2 happens to be the intersection point of those two curves here when x equals 1, y equals 2. So we're going from y equals 0 down the bottom up to y equals 2 up here. So we're taking these slices all the way across this region. So in fact, this triangle is the region of integration. So there's our region R, that triangle. So we'll use that now to populate these new limits. So again, in the new order of integration, we'll be holding x fixed initially. So imagine we're taking these fixed x values and we're integrating in y. We'll be going from y equals 0 to y equals 2x in each case. And then we'll be taking those slices then from x equals 0 to x equals 1 to get that whole triangle. So next I'll just write that a little bit more clearly. So 0 to 2x for our integral with respect to y, and then 0 to 1 for the final integration step. Now we can proceed with our integral, so let's go ahead and do that. Let's work with the inner integral first. So I'll leave this outer integral in place. And I'll deal with this inner integral. So now cosine x squared, we're holding x fixed, so this is a constant now. We're integrating with respect to y. So the integrand is going to be y cosine x squared, and we're going to evaluate that from y equals 0 to y equals 2x. That's our inner integral. So let's go ahead and evaluate that inner integral. Keep my outer integral in place. So I'm substituting in for y here as 2x. And then I'm subtracting 0 times cosine x squared, which is 0. So that is in fact the whole integral. And in fact, if we look just a little bit earlier, when we were considering the derivative of sine x squared, we find that was in fact 2x cosine x squared, which fortunately is what we have here right now. So the antiderivative of 2x cosine x squared is in fact sine x squared. So we can go ahead and evaluate straight away. So that's going to be sine x squared evaluated between x equals 0 and 1. So now evaluating, that is sine of 1 minus sine 0, which is 0. So the answer, the final answer, is in fact sine of 1 radian. Okay, thank you. See you next video.